All right. I have not posted this lecture yet. It's more than 200 pages, and I almost have only 10 pages left. So lots of elementary stuff. So I'm going to be jumping through, but I will try to finish the last 10 pages today and post them by the end of the day. Should I assume all the projects have been submitted? Including from those who have no plans to submit projects? All right. 10. So we have missing projects. And the deadline was yesterday. Okay? So we need projects. All right? So what I'm going to try to do is I'm going to go through, not as a result of my mental state today, because I'm over a million things, but I'm going to try to jump through the slides to be sure we cover some essential topics. And depending on where we are, we'll decide on Thursday if we continue with this lecture or we'll jump to state space models. The slides are very easy, so you guys can read them in detail. So I'm going to try to do some jumping here and there. So one of the things I want to discuss today, and hopefully we will have time to do it, is how do we compute parameters in HMM models? And in computing parameters, we will see that we need to integrate the algorithms for forward and backward passing, message passing. Basically, those messages will serve as essential statistics that will allow us to compute parameters given some training data. Okay, so what number was? So I'm going to be jumping slides, and I'm going to go where we stopped last lecture on slide 21, so we can do a simple training of a Markov model. Okay? So consider the problem of learning basically over sequences of words, and I'm going to introduce some probability models over a single word. So, and by the way, here the time implies sequence in a sentence. Okay, so it's not really. I mean, you can apply this, I suppose, when you talk. All right, so this can be represented words at a given time, but right now is a word within a text, basically. So this is what we call the unigram probability. This is a bigram probability. So what's the next word going to be given the previous word? And this is what is the next word given the previous two words. So we will basically see how we can train a model like that given data and do some sort of elementary statistics with some prior modeling to do that. This is an essential problem if you're interested to complete a sentence, if you want to compress basically text, and also if you want to write automatically without any interference from a human, you want to write an essay, which of course may not be reading anything, but if you write anything, somebody will buy it, right? Okay, so this is for a given textbook, all right, some reference book. This is an example of these probabilities of the unigram probabilities for the different letters. Okay, so it, in the alphabet, and the first letter is basically implies nothing, unknown. So a symbol basically that doesn't exist within those symbols. This is the bigram probability, is the transition from one letter to another. The biggest this white spaces, the higher this probability. So this is sort of like a Hinton diagram. All right, so let me go directly to the mathematical problem, and we will try to explain this in the context of sentences. The algebra, by the way, is sort of universal, even for hidden Markov models. So if you understand this, we can understand a little bit more complex models. So this is the probability. You remember, this is a Markov chain. It's not a hidden Markov model, right? So we have a chain x1, x2, x capital T. So using conditional independence relations, we write this like that. This is the probability of the initial state. So this is given. And these are the transition probabilities from state x1 to x2, xt minus 1 to xt. And I can write this in a much nicer format, the way that you see on the third line. So I want you to pay close attention, because sort of the notation is very standard for this and many other problems for mixed models and the like. So, this is a standard way to write the joint probability distribution given the parameters. And parameters here I'm referring to the probability, the initial probabilities of being on state J, and the transition probabilities AJK, transitioning from state J to state K. So look at this again. Does this make sense? In other words, is this the same as what we see up there? So how do you understand? Here I see the probability of x1. Now this is written like that. So what does that mean? The big I is the indicator function, right? So it's 1 when the argument is true, 0 otherwise. So what does this term do here? If x1 is on state 1, right, and I have k states for at all times, so if x1 is equal to, let's say, well, let's take the particular case. If x1 is the state j, so this term, what will give me? It will give me pj. And if x1 is in j, means x1 is not in all the other states. So if this product, all the other terms will give me basically a power of 0, which will result to 1. Okay? All right? So this is the way to write p of x1. And what do I have here? Here, by the way, I'm looking at a given text of length capital T, rather than all multiple sentences, each with length T. All right? So this is for one, let's say, long text that has T words. Okay? So this is a product over the sequence. This is a product over the states of J and K. And this probability of transitions is AJK to this indicator function, transitioning from J at T minus 1 to K. All right. So we are interested to compute Pj, and we're interested to compute AJK. I mean, most of the things we have done up to now, we assumed that all these parameters are known. Now we don't know these parameters, and we're going to compute them from data. So the data that I'm going to assume here would be, here I wrote this for one, let's say, sequence of words of length t, but now I'm going to have n sequence of words, each of them having a length ti. All right? So I'm going to allow basically texts of different length. So x1 will have a length t1 words, x2, t2, etc. But if you don't like that, you can take that the length of each of these is the same. So the log likelihood is given summation of the logs of each of the probabilities of xi given theta. And I'm writing it like that. So I want you to look how from this equation, the third line, I went to the top-bottom two equations. Does it make sense? You notice that the summation here in n, which is all my data sets, I push it inwards, okay? And I left the summation. So when you take logs, these products are going to become summations, right? So I push the summation over the states outside, and this summation over the data sets, I push it inside. So I get, on this term, I get this, all right? And in this term, I'm going to push the summation over n and the summation over the length of the sentences inside, and then the summations over the states, I will leave them outside. And the reason I mark this as blue is what? I mean, remember, I'm colorblind, so it's not like I'm doing it because I enjoy colors. All right, so what's the reason? We mark them for a reason here. So what you see inside this blue colors, what are they for the estimation of the parameters theta? What's the buzzword? What are we going to call this? This is where all the information from the data comes. So in estimating these parameters pj and alpha jk, the only information we need is to know these quantities in blue. So what are they? How do we call them? Now, in principle, the evidence is all of this, right? This is the evidence of the data. So, but the data, they don't come as independent entities, xij, right? They come in estimating the parameters theta inside those big summations, right? This is the only thing we need. We don't need to know the individual data. We need to know the summations. So the summations in blue are what? The sufficient statistics. So the only thing we need is to know these blue quantities. So I am going to call this nj1, and I'm going to call this njk. So with words, can you tell me what is nj1? So looking at this by, let's baptize it something nj1, because there's a j there. There's no I, I'm summing an I, and because this refers to state 1, I'm going to call this nj1. So what is this in words? What's nj1? I mean, obviously this is an indicator function, so I'm looking at all the data, all right? And I'm accounting in all my data sets, and I have n of those, n sentences, I'm accounting how many times what? The first state that I am is on what state? Well, that's state 1. And I'm accounting how many times the state 1 is on what? On j. So, for example, if j is some particular word, I'm accounting how many times the first word in the n documents is that particular word. Okay? This is, again, I refers to the data sets, right? This is the state 1 of each of the sentences. I remind you, x1 is a sentence of length ti, all right? xn is another long sentence of words of length tn, okay, t capital N. All right, what is this symbol now? What is this sufficient statistic? So I'm summing over all the data, over all the words in each data set, in each of this x1 to x capital N, and I'm accounting what in those sentences. So I'm accounting in all my data how many times at time t I was on state j, and at time t plus 1 I was on state k. All right, so if you have two words, right, how many times the state t was the word j, and how many times the state t plus 1 simultaneously was on state k. Well, so effectively, I can rewrite the log likelihood as this sufficient statistic times that sufficient statistic. And I do hope, all right, I don't have time to go through the algebra, but I want you to look sort of visually and tell me how are you going now to find the parameters pi j and ajk. This is sort of a generic inference problem for discrete distributions, so you should have some good idea on how to do this. So how do you compute these parameters pj and alpha jk? I give you the results, but how do I get those results? What did I do? So I have the evidence provided by the data. I want to compute these parameters that are coming in my model. And how do we do this? We do by maximizing the evidence. So we're going to take derivatives with respect to pi j and alpha jk. But in taking derivatives at least with respect to pi j, you also have to enhance this with something else because the pi j's are not independent of each other. If you take the sum of all the, at state, at the initial, the first word, you're going to be on some state, so the sum of all the pi j's has to be equal to 1. Right? So what we need to do is we need to sort of use a Lagrange multiplier to enforce that. So we're going to have to add here a term, lambda times the summations of the pi j's for j equal 1 to k minus 1 term, right? You see that? So we're going to have to enforce the Lagrange multiplier. So if you do that, and you take partial derivatives with respect to pi j, including the term, you will get this, and partial derivatives with respect to ajk, you will get that. Look at this now with words. These are sort of the obvious answers. Someone will say, I do not have to do any calculations because I know what the answer is going to be. but obviously we need this methodology for more complex problems. So what is pi j? What was the physical meaning of nj1 again? It was how many times in my data sets the state 1 was at word j, divided by how many times I was on anything on state 1. Not on state 1, on word 1. Okay? And similarly, what is this accounting? How many times I had transitions from state j to k versus, how many times I had transitions from j to whatever. Okay? Obviously, it's not surprising here. You're not going to count transitions from whatever to whatever, right? You have to count transitions from state j. It's basically a normalization factor from j to anything else. So actually, to make it sort of more nicer looking, I should put a k prime there and k prime. All right. So these are sort of obvious results. Okay. Now these models are computationally very difficult to work with because you remember we introduced these probabilities that for a diagram probability, basically like what we did with the inference with the parameter estimation problem. How many parameters we have to estimate here if each of the states is k? In other words, that metrics say that we computed, how big is if this is k and k? K squared. All right? So if you have an n-gram probability, this will be k to the power n. So this is computationally very expensive, and there are data sets, and I was Googling actually the other day. So one of those data sets that you can download has 50,000 words, and the number of parameters basically to calibrate the model, and this Bayesian model is 2.5 billion parameters. Actually, if you think about it, this is not trivial because the model is not computationally expensive, so it's not a bad deal. All right. All right, so can you give me a reason why we need to go away from maximizing the likelihood of the data and maybe do something Bayesian here? So in other words, can you give me sort of a situation where the model that we discussed will not work? So, you train the data with a few sentences that contain a few words, and we computed transition probabilities, and obviously you can do predictions, you can, and I will do it actually hopefully in a few minutes. You can predict what the next word is going to be. But why do we need to do Bayesian rather than maximum likelihood here? What can go wrong with, in the specific model, the language model, what can go wrong with MLE? So if, let's say, in the training sentences, one word is missing, will you ever be able to predict that word? No. Okay? So obviously there are lots of tricks you can go about this, right? And they go with different names, but I'm going to show you briefly on how we can do a fully Bayesian formulation. But before that, let me just put all of these things up here. One of the ways to sort of make this more robust is in the estimation. You remember we define in the when we estimated this parameter, say, we defined basically the MLE estimate as being njk divided by nj. Nj is basically the transitions from j to anything else, and when you sum the njk for all k's, you get, we denote this as nj, right? So a way to fix whatever problems you have with MLE is, rather than taking the MLE estimate for ajk, use some weighted average of what you computed with MLE, and also the fk, where fk is nk divided by n. So here we're interested on the transitions from j to k, But this term does what? It accounts how many times I see the word K. It doesn't really care about transitions. Okay? So, and the idea here is you select this lambda through cross-validation. So this is not Bayesian. We will see how possibly we can get something like that with a Bayesian formulation. Okay? So this idea is called, this algorithm is called the back-off smoothing. Okay? Where rather than taking the MLE estimate, you take a weighted average of the MLE estimate for bigram frequencies and also lambda times fk, where this is the unigram frequencies, which is nk divided by n. All right, so let's see how we get a Bayesian model for this. Let me put all of this thing up. Actually, this is very simple, but assumes that you know something about Dirichlet distributions as priors. So this is the sequence of words that were given. All right, so these are our training data on the bottom. And this is the metric A that is being shared by all my observations. So that's why you see these links like that. And each of this is the rows in the A matrix. So if you think, let's say, row 1, this will give me the probabilities to transition from 1 to state 1, from 1 to 2, from 1 to 3, 1 to 4, etc. So the sum of all of these things is equal to 1. Okay? So again, this will give me the transition from, from 1 to all the other states. Okay? And so what I'm going to do is I'm going to take that each of these rows of unknown parameters is sort of they're independent of each other. And what I'm going to do is I am going to put a prior on each of these rows, okay? And this prior is going to be a Dirichlet distribution that looks the way that you see here. The coefficients basically from 0 to k have been written in an interesting way where I have the sum, explicitly, I'm not going to go through the details, but basically A0 comes everywhere, and then I have M0 to Mk. So this is, if you compute the mean of this Dirichlet distribution, the mean comes to be M. Okay? And the strength of this is defined by this coefficient alpha 0. Okay? So this is the prior I'm going to impose on the model. So let's see what this is going to do. So this mean satisfies the sum of MKs has to be equal to 1. All right, so this is the prior. And I claim that the posterior for each row, alpha j, and I remind you, each row of alpha j contains the transition probabilities from j to 1, to j to 2, j to 3, right? All of these things. Do you see actually, okay, so this is the Dirichlet prior. Do you remember what form it has? So if I look at the analytical expression, let's say for alpha j1, so the term alpha j1 is going to be some alpha j1 to some power. What's that power? You guys have your computer in front of you. If you have a Dirichlet distribution, how does it look like? If you have a Dirichlet distribution and some parameters, theta 1, theta 2, etc., you're going to have theta 1 to what power? To this minus 1. And theta k, it will be theta k to this power minus 1. All right? Can you relate this with the likelihood that had the same form that we had before? That there were the parameters to some power? You remember the likelihood? I don't want to go back 20 slides, all right? You remember? So you can see now why Dirichlet distribution is the appropriate conjugate prior, all right? So you multiply, so here with pi j to some power, and here with ajk to some power, and for all k's and all j's, this will give you a Dirichlet prior, basically, okay? So at the end of the day, if your likelihood is a Dirichlet distribution, if the prior is a Dirichlet distribution, the posterior will come to be a Dirichlet distribution, and the posterior will have the same form as the prior with updated parameters, and this will be the form of the alpha j, so it will be a Dirichlet distribution with parameters alpha 0 times m that comes from the prior, and mj, where in this case this is sort of a different symbol, not a scalar mj. Mj is the vector of the time you transition from state j to state 1, from state j to state 2, and nj to state k. Okay? So the posterior distribution looks exactly in closed form the way that you see there. Okay? So now I want to basically discuss two things. How we're going to use this basically to do a better estimation and prediction for the language model. That's one thing. And secondly, how do you actually can go and assume something about alpha 0 and m? Okay? So how do you find these parameters in the prior that make sense? All right. So we're going to use the posterior mean for alpha jk. So each of this is a Dirichlet distribution. We're going to use the posterior mean, and the posterior mean basically for this distribution, if you take each of the coefficients, the k coefficient, it will be njk plus alpha 0 mk divided by nj plus alpha 0. And, okay, so njk is the frequency of transition from j to k times nj. This is what we came with Melie estimation, plus alpha 0 times mk, nj plus alpha 0, and I can write this expression like this, where lambda j is alpha 0 divided by nj plus alpha 0. So basically, this approximation that people introduced before, it comes out to be actually the posterior mean when you use the Dirichlet prior on the rows of the transition matrix AJK. Okay? So the posterior mean, right? And because the states here are either 1 or 0, the posterior mean really is the transition probability from state J to state K. Okay? So lambda J here, it is defined explicitly in terms of the prior strength, alpha 0, and also the number of times you were on state J, on the word J. Okay, so now the question is what alpha and mu is going to be, okay? And that is not a trivial problem. If you took the course with me in the fall, I trust you remember nothing. So I'm going to repeat something that I note somewhere on my slides in the fall, okay? Where for a Dirichlet distribution or a multi-nully distribution, it comes to be the same thing at the end of the day. The likelihood, all right? You remember the metrics say we assume that each row is independent of each other. So the likelihood basically is the product over all the rows of this interesting ratio of beta functions. So if somebody tells me from where this is coming, I will be very happy. So if you remember, we multiply, all right, we multiply a prior that had the strength alpha, all right, and then we got a posterior that it was also a Dirichlet distribution, and the strength was really nj plus alpha. So where did this formula come? So we have a likelihood model, which is really an anormalized Dirichlet distribution. We multiply with the Dirichlet prior, and then we set the result, the posterior is a Dirichlet distribution as well. So where this, I can tell you, it reminds me very much the normalizing factor of the Dirichlet distribution. So where did the term 1 over b alpha k? This is really the normalizing coefficient of what distribution in our problem? You remember we had the likelihood, we assume a prior that's Dirichlet, so where this term in the denominator came from? That's the normalizing factor of which distribution? So it's the normalizing factor of the prior, all right? Then you get sort of an anormalized posterior, and to normalize it, you have to multiply and divide by this factor. So 1 over this times whatever you got as a product will give you a Dirichlet posterior, and this would be the normalization factor that's left out. So the product over J of all the rows of the transition matrix of this ratio will basically give you explicitly the marginal likelihood. And what you can do is, if you are interested, to actually now go and compute these parameters, for example, alpha, what you can do is you can do an optimization problem, and you can find the actual calculations semi-analytically, basically, in this paper by Minka, using this expression to compute these parameters. All right, so let me go back to this expression. The posterior comes for each row of the transition matrix to be a Dirichlet distribution. So the transition from J to K has this mean value, and this mean value is the weighted average basically of the diagram frequencies, if you like, and this MK that has to do with the prior. Now I remind you that if you do this empirically, people will take this coefficient MK to be how many times you have the word K in the data sets, right? So here is, you have flexibility because MK is defined in terms of the prior. So the question is, what do you take as MK? So here's what is recommended. Don't read anything what it says. Look at this equation here, and it says MK is proportional to J such that NJK greater than 0. Can you tell me what this says with words? Take as MK what? Not how many times you see the word J, but what? How many times you transition to the word K from any other word J? Okay? Because in essence, this is a much more important entity rather than how many times you see a given word. Okay? And there is an example in Murphy's book that effectively it plays with two words, U and C, okay? And you notice the word C here always comes after U. So if you try to find the transition probabilities basically from U to something and from C to something, C always comes after U, all right? And you will notice the times that U and C appear in this model, it's about the same, okay? I trust it says 11 times, is the same. But U transitions more often after arbitrary words, language U, has U, couplet U, etc., C, U, whatever, but C is always given after U. So anyways, in this model, if you account that this transition probabilities is the weighted average of these diagram frequencies, and how many times you transition to the word K, okay, defined by this definition, this model performs way better than the any other sort of known estimate for MK. The best language model, if I understand, is basically a non-parametric model, and usually those non-parametric models use particle filter techniques. So you can think, since you're interested in model the transition from one word to another, basically you can think of this as time, so you can use ideas from sequential Monte Carlo to do that. And also this non-parametric methods, rather than using, if I can go back here, rather than using a Dirichlet distribution as a prior, the prior, you know what it is? It's a Dirichlet process. And I don't know if any of you will do a project on this. What's the difference, not mathematically, but if I go from this Dirichlet distribution to a Dirichlet process, what the Dirichlet process in general will allow me to do that this particular model would not allow me. Anybody knows? So in this case, right, I have transitions from J to state 0 to K, all right? In a Dirichlet process, I'm going to be able to have transitions to how many states? Infinite. Okay? So that way, words that you have not seen will be accounted in the prior model, because you have transitions to everything. Okay? But right now, so this will not allow you to do this. So the Dirichlet process is, that's why they call it a non-parametric model, because effectively you have infinite parameters to define this model. So if you are interested, the word of Tech from Oxford basically is the one that has produced one of the best language models, basically using Dirichlet process priors for doing that. Okay. By the way, let me mention something else here. If you take the Dirichlet prior to be a Dirichlet prior with coefficients 1, 1, 1, 1, do you know what is going to happen at the end of the day on this estimate? Because this is a trick that everybody does, and it goes, you will see this empirically written in lots of machine learning books. So before I remind you that the estimate of AJK was NJK divided by NJ. So if my Dirichlet prior has coefficients 1, 1, 1, 1, okay, all ones, what actually this thing is going to come to be, and what is this? What will happen to the mean of Dirichlet prior with coefficients 1? So it will come up that this coefficient here will be 1, and this will be 1. So effectively what you will be doing in computing the posterior mean, you will be adding the quantity 1 on the empirical counts. So if one word, for example, doesn't exist at all in the training data set, you will still get 1 there, so the transition from J to that word will not be 0. You're not going to get anything weird, because the regularization, that prior, will allow you to have a transition to a new word. Okay? And this goes with, let me see what the name is, N plus 1 or something. This is very typical. Somewhere I remember. Well, everyone's morphing. Okay? So this is the buzzword basically that goes with this. People use this empirically, but basically using a Dirichlet prior with coefficients 1, 1, 1 will do the job. Okay. So let me jump to slide 83 now. So we'll go back to some familiar territory, okay, and discuss a little bit about hidden Markov models, review very fast the forward and backward message passing, and then see how we can do parameter estimation on a hidden Markov model, which is a little bit more complex than the Markov chain that we discussed before. So here we have an evolution of the states the way that you see here. These are my Z's. These are the observations I have. And the purpose of introducing sort of this latent representation Z is because it allows us to take very complex dependencies between the axes now. Okay? So even though given, let's say, this Z, this observation and that observation are independent of each other, all right? If somehow I integrate all the Z's out, okay, all the x's depend on each other. So this is a much more complicated model than the Markov model, even though condition on Z, you have condition, this CI independence relations that simplify the problem. Okay, so let me just write the probability distribution. It's going to look like the joint of X and Z, okay, is Again, the probability of being on state Z1. We have the transition probabilities exactly as in the Markov model, and then we have the observation probabilities. So at each time, the probability of xn given Zn. So in the HMM model, we will take the state Z to be discrete, but the observation sex can be anything you want to. So it can be Gaussian, can be multi-nully, can be any sort of distribution. If you make this distribution to be a Gaussian and this to be a Gaussian, then you get linear Gaussian models basically that we will see later on. And from there you can get ideas similar to Kalman filtering. But right now we're going to take that this is a discrete distribution. This can be, we will leave it on the air so it can be anything we want to. All right. So this is sort of extremely similar to a Gaussian mixture model, okay? The only difference, so imagine that we have these Z coefficients, right, are the mixture coefficients that tells you when, so let's say the probability of xt given the state is a Gaussian, right? And maybe in our mixture model we have 3 different Gaussians, right? So k equal 1, 2, or 3. So what you see here is a data set that comes from 3 different Gaussians, okay? But in hidden Markov models, is a little bit more complicated because Z1 and Z2, they're not arbitrarily selected. It's not like this point will come from this Gaussian distribution or that point will come from another Gaussian distribution. Z2, whatever value it's going to take, it will depend what was the previous value. So what are those lines that you see here? So I have 3 Gaussians here, but what are these lines? So let's say I start, I am in state 1, and I say give me now x1 given z1, it gives me this. Then I say compute the state of z2. There is a high chance that z2 will remain still on this Gaussian, and then you sample again 0.2, let's say on this Gaussian, but once in a while, we'll say, you know what, the state z2 is going to be on this red Gaussian. So you start taking samples from this, until once in a while you find yourself on this Gaussian. So what's the difference of this from a Gaussian mixture? The difference is very simple, that the Z states are basically now a Markov chain. Right, so from what state you sample next depends what state you were before. All right, so in many ways, this is very similar to a Gaussian mixture model, beyond the fact that the Z's, all right, are connected through the Markovian property, basically, a transition of the probability of Zi from Zi given Zi minus 1. What you see here, it constrains on how we go from, from one state to another. Can you tell me if I want to generate this data, given all these probabilities, how are you going to sample this distribution? Can somebody give me an idea? In other words, if I want to start generating this picture here, and each of these observation models is a Gaussian with its own mean and variance, how are you going to generate a picture looking at this distribution? What's your algorithm going to look like to generate data the way that you see we're showing the picture? So how are you going to generate the observations that we saw there from Gaussians? You can see here. So what do we do? What's the first step? Take a sample from this distribution of Z1, the initial state. All right, I got it. What's next? So you took that, all right? The next thing is, can we sample now X1? Right? The answer is yes, we can sample X1 given Z1 from this probability. Okay? What's next? We already have a sample of Z1 now, so given the sample, what are we going to do? Sample Z2. Now, given Z2, we can sample X2, etc. So basically, you will get this picture that you see on the left. Okay? So it is again exactly like a Gaussian mixture. The only difference is in a Gaussian mixture you don't have this transition probability which we have here. Okay. So let me go directly because we're running out of time. If I can see. Nope, I don't see it. I have to use your imagination now because who knows what slide is down. Okay. All right. Will you agree with me that I can write the initial probability of Z1, because eventually we're going to be interested to do inference of the parameters in this distribution. I can write it like that. So look at this and tell me exactly what this equation gives me on the bottom. So I'm assuming here that the state Z1 is discrete, takes k states. So what is pi k? Is the probability that at step, let's say 1, I am on what state? K. And where is this coming? Because these discrete variables z, they are really 1 or 0. So I'm going to get pi k here when zik is equal to 1. I mean, I here refers basically, I should not have it here, but I refers basically to, no, actually, you know what? This should not be an I. What should this be? 1, right? So when the state, you know, I'm looking at one data set here, right? When Z1 is on state K, that will imply, that's the notation I use, that Z1K is equal to 1, okay? So when Z1K equal to 1, this will give me PK, and all the other terms we have an exponent 0, so will be equal to 1, so I get basically that this is equal to pi k. All right, how about this? Does this make sense? All right, this is exactly basically what we had for the Markov chain, right? So there's nothing different. This is the transition from J to K, and J and K are k-dimensional, right? They can take k states. And on the exponent, just to make this explicit, I have Zn minus 1j. This is equal to 1 when the n minus 1 state is on J status, and this when at time step n, I'm on K, all right? So if this is the case, the exponent is equal to 1, and this gives me ajk, the rest gives me a 0 exponent, so I get a contribution of 1, so nothing changes. Okay, so here's what we're interested in. We'll be interested to calculate for the hidden Markov model these coefficients and also the initial probabilities pi k. But also we need to introduce an observation model, and this observation model, we have its own parameters, and we need to compute those as well. Okay? And you know, we can consider sort of different choices, and it's later on the slides, but you can imagine if you are on state k, let's say, then these coefficients can be phi k, and this will be a Gaussian corresponding to that k state, having some mean on its own, marked by k, the index k, and some variance also of its own, and we're going to have to compute all the means and the variances of the observation model for each of the k states. But also, you know, if this is a discrete model, it can be a multi-nully distribution, so we have to calculate the probabilities of the different states as well. So I'm writing this in general like that, okay? So, so tell me, what do we have here? So I am looking at the emission probabilities. This is the observation model at step n, all right? And it says xn comes from this model, this probability to power z and k, and z and k equal to 1 happens when at step n on state k. So if I'm on state k, this is equal to 1. So the parameters basically that define the observation models are the parameters phi k, and this is what we need to observe. What we need to compute basically when we do MLE or Bayesian inference. All right. So the joint probability distribution of both the observed variables, and I call all of these variables x, so from x1 to x capital T and z1 to z capital, subscript T, is the initial probability, these transitions of the state, and the observation model. Can you tell me what is difficult basically from what we have seen on the Markov model here? Why is this a difficult problem? If you look on the left-hand side, what is different from what we had in the Markov model? You remember in the Markov chain we had the likelihood of the observations x, but now here I have the joint likelihood of x and z, given the parameters. So what is different here? Do we know z? We don't know z. Z is unobserved. So basically this joint log likelihood, it looks nice, it looks exactly like a Markovian model, but unfortunately the states z are not known, so we cannot go and do an MLE on this. It will not work, right? So what I'm going to do is I'm going to try to find, because we're lacking time here, I'm going to find directly on how we're going to do sort of an MLE for this model, working with this joint log likelihood, because computation it looks very, so computation is very easy to look at and manipulate, but we don't know what z is. So let's go to slide 170 and see on how we can compute all these unknown parameters for our HMM model. So the algorithm that we covered in last spring, and I'm going to review it basically in the context of the HMM, is based on the expectation maximization algorithm. Okay? So what we're going to do is we're going to try to sort of optimize, maximize not the log likelihood of the joint log likelihood of the observations and the hidden variables, but the expectation of the joint log likelihood with respect to the posterior distribution of z, given the observation set. And of course, the posterior distribution of z given the observations is not known because we don't know the parameters. So what we're going to do is we're going to try to iteratively update the parameters as follows. We're going to take some previous iteration, fix the parameters to some values, and then try to compute this posterior of z given x with the parameters fixed, then compute the expectation of the joint log likelihood, and notice these parameters here are parameters that are unknown and I'm going to update. So first step, I'm going to compute this expectation using this posterior that is approximated using some the previous iteration of the parameters. And then once I compute this, I am going to maximize this with respect to parameters theta. Okay, so effectively, I am going to address the complexity that has to do with the fact that I don't know z by still using the joint log likelihood of x and z, but somehow transforming this to an optimization, an iterative optimization problem where I work with the expectation of the joint log likelihood, expectation with respect to this posterior, and somehow iterate on the parameters theta and at the same time updating this posterior of z. Makes a little bit of sense. So this is sort of the standard expectation maximization algorithm for any sort of problems where you have parameters and you have some hidden variables, right, that you don't know what they are, but somehow working directly with the joint log likelihood is a much easier proposition than working with the likelihood of x. I mean, you can imagine here, if you put the summation on z directly on this distribution, this is computation intractable. You cannot do anything about it. Okay? You will have a hard time basically to come up with any algorithm, but this is, especially when you take the log, this is a very easy distribution. Taking the average with respect to this posterior is going to be easy, and the key thing here is compute this posterior iteratively using an old set of the variables of these parameters, and then when you do this computation of this quantity q, optimize with respect to theta, then come back and update this, recompute this, take another optimization with respect to theta. So 2 steps, one has to compute this expectation, that's the A step. Second, maximize with respect to theta, and hopefully you will achieve some convergence in a few iterations. So I am going to sort of try to motivate you why we need this forward and backward passing messages that we discussed, for chains, and we did this with the junction tree algorithm, etc. It comes out, okay? It comes out when you try to calculate this expectation of the joint log likelihood. You're going to need some sufficient statistics, and those sufficient statistics basically will be probabilities that we have computed from the forward and backward passing message algorithms. So the sufficient statistics that we will need is this probability, okay? And so X is all the data in the chain from X1 to X with subscript capital T. So this is the smoothing distribution that gives me the state ZT given all my X's with the parameters fixed, all right? And I remind you the symbol we use for this is the backwards gamma message, not the beta message, right? This is the smoothing distribution of ZT given all the data. And the other sufficient statistics we will need is the joint probability distribution of ZT minus 1 and ZT given all the data. So this is a joint smoothing distribution that gives me Z at T minus 1 jointly with ZT. So it comes out that to compute the E step and do this expectation calculation, you will need to compute these two probabilities, and that requires a backward calculation of messages, and this basically requires a backward and a forward message calculation. Okay, so that's another use of where these messages are coming. If you want to find the parameters in your model, you have no choice in the EM algorithm but to calculate these forward and backward passing messages. I'm going to show you where these things are coming, but this is the big picture. So let me just put a plot here that Suvik make. The algorithm, basically, you start with some values of the parameters. There's lots of guidance we want to use to start with. You compute this posterior, okay, of all the states given all the data and the previous parameters. You calculate this quantity Q, which is this expectation supposed here of the joint log likelihood. But you notice here in the log likelihood, you have theta, not theta all right? So whatever you're going to get is going to be a function of theta. Then on the M step, you maximize with respect to theta. If you converge, you are done. If not, you come back, you update the parameters, you compute a new posterior, a new expectation of the joint log likelihood, you maximize that, you keep iterating until convergence. All right. So, all right, let me see how the calculation will look like. So this is the joint log likelihood, right? And right now the observation model can be anything you want to, okay? So I want you to look at this expression, and this is, I define gamma, so let me go back so you guys can see it again, all right? So I define gamma, this is the backward message, is the smoothing posterior of zeta t, all right? And you remember zt is a discrete variable. So for example, if I put here gamma of zeta tj equal to 1, you know what this is equal to? Is the probability that zeta tj will be equal to 1, but is also the expectation of zeta tj. Why? Because zeta tj can only take values 0 or 1. Let me explain this again, right? So this is a vector zt, right? But this can take values, the zt, 1, 2, whatever states I have at each time I have k different states, right? So I can write this in a more easier format, and I say gamma of ztj which is the probability basically of ZTJ being equal to 1. And I claim that that is also the expectation of ZTJ, because if ZTJ can take values only 1 and 0, the expectation is the same as the probability. Correct? So effectively, what I claim is that if I look at the expectation of this, all right, is the same as the probability, simply because zeta tj or zeta tk has the values 1 or 0. Okay? So this gamma and the xc, which is the joint smoothing distribution of zt minus 1 and zt, they are really nothing else but posterior expectations of the ZTJ variables. You remember my definition of gamma z, right? What was it? It's a posterior distribution, is the posterior of zeta t given all my data. All right? But I'm just telling you that this posterior distribution is also the expectation of each of the ZTK values. Because each of the ZTK values, if you try to find the expectation, how do you compute the expectation of a variable? If it takes value 1, would be 1 times what? The probability that it takes the value 1, plus 0 times the probability that it takes 0, forget about it. So this is also the expectation. So, can you look at this equation here now and tell me how from this equation, when I take logs and then expectation, I get this equation? From where did that come from? So I took logs of this, and you remember we wrote this nice equation with the transition probabilities to the power, right? And we can do this, the same thing there. But how did I get a gamma there? Let's concentrate on this. How did I get a gamma? What is gamma Z1K? I mean, gamma Z1, right, is the posterior of the state Z1 given all my data. So what is gamma Z1K? Is the probability that at time 1 I'm at what state? K. And because that I can only be in state 1 or 0, this is also what? Is the posterior expectation of Z1K. So how did I go from this term to a gamma times log of pk? You remember this term used to be pk to a power that gamma Z1K is equal, the indicator function that Z1K is equal to 1. So I'm getting the expectation of that. And what is that expectation? Is gamma Z1K. All right? So similarly, this in the transition from t minus 1 to t, you will get basically this quantity xc, which is the smoothing joint posterior of zt minus 1 and t. So what is this actually? This is the expectation of what distribution? I mean, what variables? This is the joint distribution of zt minus 1 being on state z and zt being on state k. The posterior expectation of that is basically that quantity c. Okay? So the point here is, right, that these gammas that we computed in xc and that we define them as posterior distributions, all right, this is how we define them, okay? These are vectors because ZTE can take value 1, I have different k states, okay? So when I simplify this, and I'm asking what is gamma ZTK, yes, that is the posterior of ZTK being equal to 1, but is also the posterior expectation of ZTK. Similarly, when I put this ZT minus 1J and ZTK, yes, that is the joint probability, posterior probability of ZT minus 1 being on state J and this being on state K, but is also the posterior expectation of those two variables. And so when you take this joint log likelihood, all right, you take the joint log likelihood, you will get this indicator functions on the front when you write this ajk, and on the top you're going to get the indicator function that zt minus 1 j equal to 1 and ztk equal to 1. Then when you take the logs, this will come in front of, in front there, all right? And then you're going to have to take expectation of that. Why expectations? Because what did we say? That we cannot operate with the joint log likelihood. We have to take expectations. Okay? We have to take expectation with respect to the posterior of z, and those expectations give you basically the sufficient statistics, and those sufficient statistics come to be nothing else but this backwards message is gamma, and this, so this is moving distribution basically, and the joint posteriors of zt minus 1 and zt, and I have similar thing here for the observation model. So there's nothing really fancy. On the first term, I'm going to have k states, so I'm going to get a summation. Here I'm going to have these steps totally, all right? This is this product. And I have transition from k possible states to k possible states, so get a double summation, and this is the sufficient statistics. You get log of ajk, and here you get again these gamma coefficients, and this is the log of the observation models, considering that I'm on state k, so the parameters corresponding to the observation model will be here 3 with subscript k. So I don't know if anybody remembers, but what is the meaning we have given, what is given in the literature to this posterior probabilities gamma of z? You remember when let me back up, right? When we did the Markov chain, and we did not write the expectation of the joint log likelihood, there was only likelihood there was no z. But what did I have on a Markov chain instead of having here gamma of z 1k? What did we have on the Markov chain? Do you remember? What were the sufficient statistics on the Markov chain? Yes, which is the time, the number of times that the first, let's say, at the, at time 1, I'm on state k. Correct? So in the Markov model, again, here I had a quantity that was telling me how many times at step 1 I am on state k. So what is now the meaning of this quantity here? Because this is a posterior quantity. So this is after I have observed the data, right? Is what is the expectation of the times that I will be on my time step 1 on state k. This is what we call the, what's the word that we use or is used in the literature? Well, similar to what we use, especially if you remember on how you do the EM algorithm for Gaussian mixtures. Look, I'm looking, what type of things you get. Frequency, okay, nope. It starts with an R. Are the posterior responsibilities? All right? So basically, this is, looking at the data, right? And I'm looking at state 1, this accounts sort of in a posterior setting how many times my state 1 is, my time 1, data, if you like, are on state k. This is similar to what you have on Gaussian mixtures. That's what's called the posterior responsibility. So, so let me just summarize again, right? So we want to work with, in learning the parameters, and the parameters here are implying this pi, this a, and this coefficients phi in the observation model. We want to work with the joint likelihood, because computationally is very easy, right? This is a discrete model. This, let's say, it's a Gaussian. It's very nice, okay? But we don't know what z is. So how can we compute pi when we don't know z? So the idea is, yes, start with this, but take the expectation with respect to the posterior of z, all right? And then there's still one more complexity, but how can I do this when that posterior depends on the parameters pi and a and phi? So the second step is, well, start iterating on these parameters. So fix them to something, then compute the expectation of this with respect to the posterior given the parameters, all right? This is what you see here. Then when we have this quantity, what are we going to do to this quantity now? We're going to go and take derivatives with respect to pi k, alpha j k, and with respect to phi k, right? And we'll keep doing iterations. So this actually, at this step, it looks identical to what we had for Markov chains. There's really nothing that is different, okay? So you can go and introduce Lagrange multipliers to enforce that the sum of pi k is equal to 1, and then take derivatives with this. And I can tell you the answers on this maximization step. They're sort of identical to what we did for a Markov chain, but the meaning of the symbols is very different. So what we get, so remind me, what did we get for a Markov chain? What was pk? So we trained the model, so what was pk coming to be? It was the time, the number of times, let's say at time 1 I was on state k, divided by the time, by the number of times at time 1 I was in any other state, in any state, okay? So here what do I have? Since I have observed data, pi k is, the posterior is the expectation, right? That at time 1 I'm on state k, divided by this posterior responsibilities that at time 1 I'm in any state j from 1 to k. And similarly, ajk is defined by these posterior transition probabilities that, so in this case ajk, so that at time t minus 1 I'm on state j, and then I transition at time t to state k. So this is exactly what we had before. The only difference is that this xi and gamma are posterior probabilities, and they're smoothing probabilities because here, to calculate both gamma and xi, you account for all the data from time, let's say 1 or 0, all the way to capital T, okay? So these are smoothing probabilities, not predictive probabilities. So it's not something, you collect data to here and you estimate what this is. Okay, here is, you go all the way, all right, and then you say, now, can you tell me what's the expectation or the probability of z1k being equal to 1, and it's given by this entity, so that will give you pi k, etc., etc. And so we can close because it's 144 on this. And how do you calculate then the parameters in the observation model? So you remember there is an observation model here as well. So if this is a Gaussian, not a big deal. So I'm going to give you what the formulas come. So the mean of this Gaussian, and maybe here you can appreciate why these are posterior responsibilities. So the mean of the Gaussian comes to be like this. So look and extrapolate why this is sort of a posterior responsibility. Here I am using all the observations at all times, right? But I'm weighting this with this gamma. So what does that gamma do? It says how much responsibility the data time t takes for belonging to the state k. Right? So obviously, I mean, this is a good way to see that sort of this is a posterior responsibility because I am counting all the data, right, in my sequence, and I'm weighting them with these probabilities, which are the posterior probabilities. And similarly for the variance, basically, it is like, you're estimating a Gaussian, all right, you are using all your data, okay? This is with respect to this mean, by the way, all right? This is very important. And again, you weight this with respect to the responsibilities that the data time t belongs to state k. You can extend this to actually to other distributions. So if you have a multinomial or a Bernoulli distribution, many other things, sort of, you can work the algebra right away. So what maybe I will do on Thursday is I'm going to go back and bring it to the need basically for computing the smoothing distributions. So lots of people think these smoothing distributions sort of, they're not, nobody wants to use all the data. They are interested in all line estimation, right? But you can see when you do the expectation maximization algorithm, you really need to have this posterior responsibilities and these joint expectations, and those require that you use all the data, so there's smoothing distributions. So we'll discuss on how with message passing we can compute them. I'm going to post the slides today, so look at them. Sort of, things look very complicated, but I think in many ways the HMM model is the simplest. Okay, so you should invest some time to understand what